Welcome to the course on Introduction to Electrical Engineering. We will have lecture 41 on electrical measurement part 2. So, starting from outline of presentation today, introduction, dynamometer type instrument, moving iron instrument, then electronic voltmeter, AC electronic voltmeter, cathode ray oscilloscope, CRO. Then we will talk about exercise and numerical problems followed by references. So, coming to the introduction of today lecture. So, here we have electrical testing in the home as you could have seen, then lab testing, then of course, we require instrument for that purpose, control panel with voltmeter and ammeter, then the technician testing contact point on circuit board with voltmeter, then the electrical switchgear testing, then the real automation and protection relay testing calibration, and the close up of man using voltmeter in factory, engineer testing satellite disk, then the measuring battery voltage, then checking the voltage on a rooftop photovoltaic power plant, and the universal voltmeter and electronic measuring device, and the power cable fault locating and testing, then the low voltage and PAT testing, then relay and protection testing, then transformer testing, then water leak detection, then battery testing. Now, coming to how this really we use the different instruments, coming to classification of electrical measuring instruments according to the effect. We discussed like a moving coil instruments, moving iron instrument, then induction instrument, then electrostatic instrument, then electrolytic instrument and hot wire instrument. These are the effects used for this electrical measuring instrument like. Now, classification of moving coil based measuring instrument, coming with moving coil permanent instrument for DC work only. We already discussed dynamometer instruments which are used for AC as well as DC like. So, coming to dynamometer type instruments, why the magnet instrument cannot be used for AC measurement. If AC is given to these instrument and a rotating torque will be produced, because there is a magnet which gives the steady flux like. So, if you are putting like a alternating current into it, it will give a alternating or pulsating torque into it. So, due to the moment of inertia of moving system, the pointer will not follow rapidly changing alternating torque and will fail to show the anything. And the permanent moving coil instruments cannot be suited for AC current and voltage. The electrodynamic or dynamometer type instrument is a moving coil instrument, but the magnetic field in which the coil moves is provided by two fixed coil rather than permanent, and the magnetic field in the air gap is changing along with the change in current. So, it is also called as transfer instrument because it is calibrated with the DC and can be used accurately for AC measurement, and electrodynamic type instruments are used as AC voltmeter and ammeter and both. Now, coming to typically construction of this your typical dynamic kind of instrument. Here we have of course, the coil on moving as well as fixed part. So, we have a fixed coils which is divided on two sides of this, and then we have moving coil in between. So, first is the fixed coil, the magnetic field is produced by the fixed coil which is divided into two sections to give the more uniform field near the center and to allow the passage of instrument shaft. And it should be noted that the both fixed and moving coils are air cooled. Now, coming to second part as a moving coil. So, moving coil is wound either as a self sustaining coil or else on a non-magnetic former. So, a metallic former can not be used as the eddy currents will be induced in it by alternating field. So, light but rigid construction is used for the moving coil. So, now coming to leg springs. So, controlling torque is provided by two control springs, and these hair springs are also act as leads of the current to the moving coil. And now, dampers, air friction damping is used in these instrument because we do not have magnet here. Now, the shielding, the magnetic field produced by fixed coils is weaker than the other type of instrument. So, these meters need a special magnetic shielding, and dynamic instruments are effectively shielded from the effect of external magnetic field by enclosing the mechanism in a laminated iron hollow cylinder with closed hands. Now, coming to torque equation of electrodynamometer type of instruments. We have electrodynamic instrument can be represented by a equivalent circuit as shown in the figure with the two coils which have a current I1 and I2 with a kind of inductance L1 L2 with the mutual coupling and voltage applied. So, I1 is the instance value of current in the fixed coil, I2 is the instance value of current in moving coil, L1 is the self inductance of fixed coil and L2 is the self inductance of moving coil, M is the mutual inductance between the fixed and moving coil. So, the flux linkage is flux linkage coil 1 will be phi 1 equal to L1 I1 plus M I2 and flux linkage coil 2 will be phi 2 L2 I2 plus M I1 and electrical input energy will be E1 I1 dt plus E2 I2 dt equal to I1 d phi 1 plus I2 d phi 2 as E1 equal to d phi 1 upon dt, E2 equal to d phi 2 upon dt. So, it will be equal to your I1 d in bracket L1 I1 plus M typically M into I2 and I2 into d of L2 I2 plus M I1 and equal to I1 L1 d I1 plus I1 square d L1 plus I1 I2 dm plus I1 M d I2 plus I2 L2 d I2 plus I2 square d L2 plus I1 I2 dm plus I2 M d I1. So, now energy stored in the magnetic field equal to half I square L1 plus half I2 square L2 plus I1 I2 M and change in the energy stored will be d derivative of this energy, that is half I1 square L1 plus half I2 square L2 plus I1 I2 M and that will be equal to like I1 L1 d I1 plus half I1 square d L1 plus I2 L2 d I2 plus half I2 square d L2 plus I1 M d I2 plus I1 I2 dm plus I2 M d I1. So, now torque on electromagnetic torque will be from principle of conservation of energy. The total input energy will be change in energy stored plus mechanical energy. So, mechanical energy can be obtained by using the previous equation. Therefore, mechanical energy equal to half I1 d I L1 plus half I2 square d L2 plus I1 I2 dm. And now, the self inductance L1 L2 are constant, hence therefore, d L1 d L2 both are equal to 0, hence the mechanical energy will be I1 I2 into dm. So, suppose T I is the instantaneous deflecting torque and d theta is the change in deflection. So, mechanical energy equal to work done, that is T I d theta equal to I1 I2 dm and so T I equal to I1 I2 dm upon d theta. So, now coming to operation with DC, so I1 is the current in the fixed coil, I2 is the current in the moving coil. So, deflection torque is T d equal to I1 I2 dm upon d theta. Suppose theta is the finally steady deflection, so therefore, controlling torque will be Tc into Kd, so where K is the spring constant. So, operation with at finally steady Td equal to Tc, so I1 I2 dm upon d theta equal to K theta or theta equal to I1 I2 dm upon K d theta, or if I1 equal to I2 equal to I, so it becomes theta equal to I square dm upon K into d theta. So, now we can say for DCU the deflection thus is proportional to square of the current and hence the scale is uniform and crowded at the ends. So, if the in electrodynamic ammeter the fixed and moving coils are cascaded in series as you can see here. So, we can say a shunt is connected across the moving coil for the limiting the current and deflection torque is proportional to the mean of a square value of the current, thus the scale is calibrated to read the RMS value. And the typical diameter as a voltmeter. So, electrodynamometer instrument can be used as a voltmeter by connecting a large non-inductive resistance of the low temperature coefficient in series with the instrument coil. As you can see here how the large resistance connected. And the electrodynamic instrument as a dynamometer as wattmeter. So, electrodynamic instrument can be used as a wattmeter by connecting a fixed coil in series with and shunt coil in pressure coil as a volt coil. So, electrodynamic you can see how it is the instruments are connected. So, advantage is they can be used on AC as well as on DC measurement. These instruments are free from eddy current and hysteresis error, and electrodynamic voltmeters give the accurate RMS values of voltage irrespective of the waveform and precision grade accuracy of 40 Hertz to 500 Hertz. Disadvantage is as the instrument has a square law response, so scale is uniform, non-uniform. These instruments have a small torque weight ratio, so the friction error is considerable. So, more costly than the PMMC and moving iron instrument type of instrument, and adequate scaling of the movements against the magnetic field is essential. and power consumption is higher than the permanent moving coil, but less than the moving iron instrument. Now, coming to third category of instrument, we call it moving iron instrument. In moving iron instrument, the movable system consists of one or more pieces of specially shaped soft iron, which are so pivoted so as to be acted upon the magnetic field produced by the current in a coil. And these are two general types of moving iron instrument, like a repulsion or double iron, or attraction or single iron type. So, now coming to construction of moving iron instrument. So, brief description of different component of moving iron instruments is given here. So, coming to moving element, a small piece of soft iron in the form of veinage or rod, coil is to produce the magnetic field due to the current flowing through it and the magnetize the iron pieces. In repulsion type, a fixed vein or rod is also used and magnetized with the same polarity. Now, control torque is provided by spring or weight, that is gravity, and damping torque is normally pneumatic. The damping device consisted of an air chamber and a moving vane attached to the spindle, and deflecting torque produces a movement or an aluminum pointer over a graduated scale. And the basic principle is typically these instruments are being on the principle that when the unmagnetized soft iron piece is placed in the magnetic field, then the piece is attracted towards the coil. So, you have already the coil here and you have a typical balance weight and moving iron here, and working is when the operating current is passed through the coil, it behaves like a magnet and therefore, it attracts the soft piece towards it. Now, coming to deflecting torque, the force F pulling the soft iron piece towards the coil depends upon the field strength H produced by the coil and pole strength M developed by the iron piece. So, F is proportional to M H and F proportional to H square. So, T D equal to F into H square. So, if the probability of error is assumed constant, so H is proportional to I or T equal to T proportional to I square. So, now the deflecting torque is spring control, that is T equal to K theta, and in a steady position of deflection T D equal to DC. So, for DC measurement theta equal to I square proportional to I square, or for AC measurement your theta is proportional to I RMS square. So, repulsion type moving iron instrument, the principally these instruments are based on the principle of repulsion between the two iron pieces similarly magnetized, as you can see here moving piece and it is a fixed piece, and working is when the operating current is passed through the coil, the magnetic field magnetize both the iron pieces in the same direction and both pieces become similar magnets and hence they repel each other. Now, coming to deflecting torque, if the two pieces develop pole strength M1 and M2 respectively, then the instantaneous deflecting force is proportional to the repulsive force. So, since pole strength develop are proportional to H, the instantaneous deflecting torque is T D proportional to H square or H proportional to I or T D proportional to I square. So, for spring control T proportional to theta. So, in the steady position of this T D equal to DC. So, for DC theta equal to theta proportional to I square and for AC theta proportional to I RMS current square. The advantage, the robust construction are relatively cheap and suitable for measuring both DC and AC and can withstand overload momentarily. Disadvantage is non-uniform scale and there is a hysteresis error in the instrument, since large amount of power is consumed to supply I square all in the coil and magnetic losses in the vane. So, it is not very sensitive instrument. Now, coming to electronics voltmeter, the voltmeter which uses the amplifier or increases their sensitivity is known as the electronics voltmeter. The moving coil voltmeter is not able to detect the low voltage. The electronics voltmeter uses the transistor or vacuum tube. So, any electronic voltmeter has a much higher input resistance than electromechanical instrument. So, the voltmeter loading effect is considerably reduced. The electronics voltmeter use rectifier, amplifier and other circuit element to produce current, and this current is proportional to the voltage to be measured. So, we have input signal, that is input switching and ranging, then input amplifier, input switching and ranging, and then rectifier analog to distributor and then PMM. So, it is a single condition that we call it electronics voltmeter. So, the basic circuit is made of 3 stages: signal conditioning, an input attenuator, and our electronic amplifier, and the electromechanical voltmeter stage. So, you can see here we have a rectifier which convert AC into DC, then it goes to amplifier, and we have a transistor amplifier here, finally it goes to voltmeter, moving coil voltmeter. The advantage of electronics meter is low level signal detection, low power consumption, high frequency range, and low input capacitance, and no loading errors. Now, coming to AC electronics voltmeter. So, DC voltmeters measures only DC voltage. For measuring AC voltage, 2 steps are: step 1, convert AC voltage signal into DC voltage signal by using a rectifier. Now, measure the DC or average or peak value of the rectifier output signal, and that is AC voltmeter. So, first we have input as a voltage divider, then AC amplifier with the negative feedback, and then rectifier and filter, and followed by DC meter. So, type of AC electronics voltmeter. So, rectifier type AC voltmeter, average response AC voltmeter, then peak responding AC voltmeter, to RMS AC voltmeter. So, coming to first as your rectifier type of AC voltmeter, half wave rectifier circuit or rectifier instrument, a half wave rectifier is connected ahead to DC voltmeter, then the entire combination together is called AC voltmeter using a half wave rectifier. So, you can see here we rectify half and it goes to typically PMMC, and how the voltage is rectified, that is the voltage applied to this meter. The full wave rectification, rectifier is connected ahead voltmeter, then the entire combination together is called AC voltmeter using full rectifier, and this is the kind of voltage go to rectifier after rectifier to the instrument like. So, half wave rectifier means average value is V average equal to 1 upon 2 pi 0 to pi Vm sin omega t into d omega t, that is 2 upon pi Vm, and where V average is 0.318 Vm, that is 0.318 under root V, that is V average equal to 0.45 V, and full wave rectifier average value is V average equal to 2 upon 2 pi, that is 1 upon pi 0 to pi Vm sin omega t, d omega t 2 upon pi Vm, and V average is 0.636 Vm, that is 0.636 into root 2 Vm, that is V average equal to 0.9 V, and sensitivity for half wave rectifier is S equal to 0.45 SDC, and sensitivity for half full wave rectifier is your S AC equal to 0.9 SDC. Now, extension of range for rectifier instrument as a voltmeter. So, suppose it is intended to extend the range of a rectifier instrument which uses PMMC instrument having a DC sensitivity to SDC. So, V equal to voltage drop across the PMMC instrument, and capital V is applied voltage. So, therefore, for DC operation the value of the series resistance multiplied needed is RS equal to V upon IFS, that is minus RM minus RD. So, RS equal to SD V minus RM minus RD for half wave rectification, and RS equal to V upon IFS, that is minus RM minus 2 RD. So, RS equal to SDVD into minus RM minus 2 RD for full wave rectification. So, factor affecting the performance of rectifier type of instrument. The effect of waveform, the rectifier instrument is calibrated in terms of root mean square values of sine wave of voltage and current. An effect of rectifier resistance, the nonlinear characteristic of the diode may distort the current and voltage waveform. An effect of temperature change, so there may variation in the temperature due to which the electrical resistance of the bridge changes. An effect of rectifier capacitance, so bridge rectifier has a imperfect capacitance, thus due to this it bypasses the high frequency current. Now, coming to case of peak reading electronics AC voltmeter. So, peak responding voltmeter, that is peak responding voltmeter is also designed to indicate the RMS value of a sine wave, and capacitor charges through a diode to the peak value of the applied voltage and the meter circuit that respond to the capacitor voltage. So, there are two types of peak responding voltmeter, which are DC coupled peak responding voltmeter and AC coupled peak responding voltmeter. So, now DC coupled peak responding voltmeter is a DC coupled peak voltmeter in which the capacitor charges to the total peak voltage above ground reference, and in this case the meter reading will be affected by the presence of DC and AC voltage, and that is DC coupled voltmeter. And AC coupled, the AC and DC coupled detectors are same, their difference is only due to the different setup in output from the capacitor in DC and from the diode in and AC coupled peak responding voltmeter. So, advantage are the peak responding voltmeter can measure frequency up to several hundreds of megahertz with the minimum of circuit loading, and disadvantage is the harmonic distortion in the input waveform and limited sensitivity of the instrument due to imperfect diode characteristic. Now, coming to 2 RMS AC voltmeter. So, this instrument indicates the RMS value of any waveform by using the RMS detector that respond to directly to heating value of the input signal, and the 2 RMS voltmeter are unique because they are the only type that accurately measure the non-sinusoidal waveform, and they respond to the RMS or heating value of the impressed signal. The principle of working is the input signal is AC coupled, amplified and attenuated, and heats up a thermocouple, and thermocouple produces a DC output proportional to AC to the RMS value of the AC input, and this DC voltage is the amplified and deflects the meter reading needle to the RMS value, and the response of thermocouple is not dependent on the wave shape, and thus the true RMS voltmeter can accurately measure the non-sinusoidal waveform. And here is the typically coming to like a heat loss. I mean, you have here the heating element, and you have balancing thermocouple, and you have a DC amplifier. So, heating loss in temperature and thermocouple is P equal to V RMS square upon R heater, and measuring output voltage is V equal to F P as a F V RMS square upon R heater, that is V 0 equal to K V RMS square. So, K is the constant of proportionality and is a true RMS reading voltmeter. The advantage is nonlinear behavior is avoided by using the 2 thermocouple placed in the same thermal environment, and the 2 RMS value is independent of the waveform of the AC input, and sensitivity in the millivolt region are possible. Now, coming to cathode ray oscilloscope CRO, it is very frequently used in electronic circuit, especially typically in your undergraduate. So, a cathode ray oscilloscope is a instrument generally used in laboratory to display, measure and analyze various waveform of electrical circuit, and cathode ray oscilloscopes use luminous spots which are produced by stacking the beam of electrons, and this luminous spot move in response to variation in input quantity, and cathode ray oscilloscope is used to analyze some properties like amplitude, frequency, right time, distortion, time interval, etc. The components of CRO are: the CRO consists of the following: cathode ray tube CRO. So, it is some input signal to vertical amplifier, then it goes to display line, and the same typically after this it goes to triangular and time base and horizontal amplifier, and of course, to all the circuit with the CRT, and then it goes to luminous spot with the horizontal amplifier, and it is a phosphorus screen with the electronic beam and a horizontal diffraction plates, and that is the CRO block diagram of its basic operation. So, it has a vertical amplifier, it has a like horizontal amplifier, then we have a time based generator, then we have a trigger circuit, then we have power supply. So, in this the main in cathode tube, the main parts of CRO is a cathode tube which called CRT. It generates the electron beam, accelerates the beam to a high velocity, reflects the beam to create the image, and contains a phosphorus screen where the electron beam eventually becomes visible. And 3 major components of general purpose CRT are electronics gun or electron emitter, deflecting system, then the fluorescent screen. Now, this is typically the oscilloscope where you can see the typically different parts. So, we have a typically here the cathode, we have a heating filament, then we have focusing anode, we have accelerating anode, and we have a Y plate, we have X plate, and we have electronics gun, and we have a deflecting system by vacuum, and here electronic beam is brought to in bright spot. So, this is the basic building block, and we have a fluorescent screen on which this your bright spot is visible like. So, in the cathode tube there is electronics gun. The electronics gun consists of an indirectly heated cathode, a control grid, an accelerating anode and a fluorescing anode, and the accelerated electronic beam passes through a fine hole, and the negative voltage at the control grid controls the flow of electrons in the electronic beam, and consequently the brightness of the spot of the CRO screen is controlled. Now, coming to deflecting system of cathode tube, the deflecting system consists of a pair of horizontal and vertical deflecting plates. The deflection is proportional to the deflecting voltage between the plates, and that to deflect the beam horizontally or vertically, voltage is applied to the horizontal deflecting plates or vertical deflecting plate respectively. And coming to fluorescent screen, the phosphor is used as a screen material on the inner surface of a CRT and phosphor absorb the energy on the incident of electron. Then the spot of light is produced on the screen when the electronic beam hits, and the bombarding electron is striking the screen, release the second emission electron. These electrons are collected, trapped by a aquarium solution of a graphite called aqua drag, which is connected to the second anode. Now, coming to vertical amplifier, the vertical amplifier determine the sensitivity and bandwidth of the oscilloscope. So, sensitivity expressed in terms of volt per centimeter. So, gain of vertical amplifier determine the smallest signal, that is the oscilloscope can satisfactorily measure by reproducing it on a CRT screen. Now, coming to horizontal amplifier, the shift generator output can not derive the horizontal plates, it must be initially amplified by horizontal amplifier. So, voltage to horizontal plate can be applied by internal source int or external source that called external. And time based generator, the CR is used to display the waveform that varies as a function of time, and if the waveform is to accurately reproduce, the beam should have a constant horizontal velocity, and the time taken to return to its initial value is known as flyback or return time, and it typically helps to display the actual waveform of AC applied across the Y2. Now, coming to triggering, triggering controls are used to maintain the steady traces on a screen, and the display stationary wave pattern sweep voltage is synchronized with the input signal. Synchronization is the method of locking frequency of time base generator to the frequency of input signal. Now, coming to power supply, so there is a low voltage power supply. This voltage of out of V tens of hundreds of volt, it supports power amplifier, trigger generator, time based generator. And high voltage power supply supply the power to electrodes of electron gun. It supply voltage of 1600 to 22 volt, 2200 volts. Coming to laser patterns, so characteristic of patterns that appear on the screen of a CRO when sinusoidal voltage are simultaneously applied to the horizontal and vertical plates are called Lissajous pattern. Lissajous patterns are used to measure frequency and phase difference. Coming to now frequency measurement, the Lissajous patterns may be used for accurately measurement of frequency, and the signal whose frequency to be measured is applied to the Y plates, and accurately calibrated standard variable frequency source is used to supply voltage to Y X plate. Now, to determine the ratio of frequencies of signal applied to the vertical and horizontal deflecting plate, so simply draw arbitrarily horizontal and vertical line on Lissajous pattern and intersecting the Lissajous pattern, and now count the number of horizontal and vertical tangencies to Lissajous pattern with these horizontal and vertical line. So, it comes omega y upon omega x equal to f y upon f x, that is number of horizontal tangencies divided by vertical tangencies, or frequency measurement equal to omega y upon omega x f y upon x. So, number of intersection of Lissajous pattern horizontal lines and number of pattern of this. The example is here how it is cutting typically on vertical line. So, that is virtually f y upon x equal to 4 by 2, that is 2. So, frequency twice time. Example is here of others. So, f y upon f x equals 6 by 4, that is 3 by 2. Coming to phase measurement, the two sinusoidal waveform of the same frequency produce the Lissajous pattern, which may be a straight line or a circle or ellipse depending upon the phase and the magnitude of the voltage. So, when the two sinusoidal signals of same frequency and same magnitude are applied, two pairs of the deflecting plates of CRO, the Lissajous pattern changes with the change of phase difference between the signals applied to the CRO. So, for equal voltage of same frequency, progressive variation of phase voltage causes the pattern to vary from straight diagonal line to elliptical, different intensities, and then to a circle, after that through another series of ellipse, and finally the diagonal statement. So, this is here the example how typically the kind of phase, you can just have a with the typically different angles like alpha equal to 0, then alpha equal to 30 or 30 or typically of different value. Now, coming to first case of when theta equal to 0 to 90 or 270 to 360 degree, as you can see here. So, theta equal to sin inverse x1 upon x2, that is sin inverse y upon y2 from this diagram. So, case 2 if 90 to 180 then or 180 to 270, theta equal to 180 minus sin inverse x1 upon x2, that is 180 degree minus sin inverse y1 upon y2, as you can see in the circle. So, now coming to the some of the theoretical problem. State the advantage of moving iron instruments. Advantage of moving iron instrument, less expensive, can be used for both AC and DC, reasonably accurate. Why the heater wire of thermocouple instrument made very thin to reduce the skin effect and high frequency. The reason why eddy current damping cannot be used in moving iron instrument, they have a strong operating magnetic field. They are not normally used in vertical position. They need a large damping force which can be only provided by air friction. So, they have a very weak operating magnetic field, and introduction of permanganate required for anti damping will distort the operating magnetic field. A 0 to 10 milliamp meter reads 4 milliampere in circuit. If button control snaps suddenly, the meter will now read, it will go to reset, that is 0 milliampere. The expression as the spring is connected in series with the coil. So, the spring snaps, the current in the coil is 0, hence the PMC meter will read 0 value. Now, coming to the solved problem, starting with the first problem, a moving coil instrument gives the full scale deflection with 15 milliampere and has a resistance of 5 ohm. Calculate the resistance required in parallel to enable the instrument to read up to 1 ampere, in series to enable the up to 10 volt. The current through the coil as shown in the figure here equal to I equal to potential difference between across the coil divided by resistance of the coil. So, that is putting value 15 by 1000, that is potential 11 volt divided by, so PD will be across 0.075 and from the current as equal to a total current minus the current through the coil. So, that is your 1 minus 0.015, that is 0.985. So, current through shunt, that is 0.985 equal to 0.075 divided by resistance of the 17 ohm. So, resistance of S equal to 0.076 into 16, so 76 milliohm. And from this figure, so current through coil, that is PD across TT, I mean here, and that is resistance between the two. So, that is 15 upon 1000 equal to 15, 10 upon resistance between TT. So, resistance between TT will be 665.7 and the resistance of resistor required in series with the coil, total resistance TT minus resistance of the coil. So, that is 66.7 minus 5, that is 61.7 ohm. Now, coming to example 2, the inductance of 25 ampere electrodynamic ammeter changes uniformly at the rate of 0.0035 microhenry per radian. The spring constant is 10 to the power minus 6 Newton meter radian. Determine the angular deflection at full scale. So, since dm upon theta equal to 0.0035 into 10 to the power minus 6 Henry per radian, now the deflection theta equal I square upon k into dm upon d theta. So, angular deflection full scale I equal to 25 ampere is given. Now, theta equal to 25 squared y by 10 to the minus 6 into 0.0035 into 10 to the power minus 6 into 180 divided by pi, that is 125 degree. Now, example 3, in electrodynamic instrument, the total resistance of the voltmeter coil circuit is 8200 ohm and the mutual inductance changes uniformly from minus 173 microhenry to at 0 deflection to plus 175 microhenry at full scale. The angle of full scale being 95 degree. If the potential difference of 100 volt is applied across the volt circuit and the current is 3 ampere, the power factor of 0.75 pass through the current, well, what will be the deflection? Spring constant of instrument is 4.63 into 10 power minus 6 Newton meter per radian. Change in mutual inductance Dm equal to 175 minus in bracket minus 173, that is 348 microhenry. So, deflection theta is 95 degree, that is 1.66 radian. So, range of change of mutual inductance dm upon theta equal to 209.63 microhenry per radian. So, current through the coil I1 is 3 ampere and current through I2 is 100 upon 82, and that is 0.0122 ampere. So, power factor is 0.75. So, deflection is I1 I2 1 into k into cos phi dm upon d theta. So, putting this value, so theta comes 1.242 radian or equal to 71.2 degree. Now, coming to example 4, a 50 volt range spring control electrodynamic voltmeter has a initial inductance of 0.25 Henry. The full scale deflection torque is 0.4 into 10 power minus 4 Newton meter and full scale deflection current of 50 milliampere. Determine the difference between DC and 50 hertz AC reading at 50 volt. If the voltmeter inductance increases uniformly over the full scale of 90 degree. Full scale deflection is 90 degree. Full scale deflecting torque TD equal to 0.4 into 10 power minus 4 Newton meter. Full scale deflecting current is I equal to 50 milliampere and initial inductance M equal to 0.25 Henry, and so deflecting torque is I square upon k into dm upon d theta. So, full scale deflection equal to 0.4 into 10 power minus 4 equal to 0.05 square dm upon d theta. So, dm upon d theta is 0.4 into 10 power minus 4 into d theta, that is 0.016 Henry per radian. So, total change in inductance for full scale deflection dm equal to 0.016 into 90 upon into pi by 180, that is 0.0251 Henry. So, total mutual inductance is m equal to 0.25 equal to 0.0251 0.2751 M. The resistance of voltmeter R equal to V upon I, that is 50 upon 0.05, that is 1000 volt ohm, and impedance while measuring the voltage 50 hertz. So, Z equal to your typically your R square plus your 2 pi L M square, that comes 1004 ohm, and volt reading will 50 upon 1004 into 1000, that is 49.8 volt, and therefore, difference in reading 15 minus 49.8, that is 0.2 volt. Now, coming to example 5, the inductance of a 20 ampere electrodynamometer dynameter ammeter change uniformly at the rate of 0.0035 microhenry degree, and spiral constant is 10 power minus 6 Newton meter per degree. Determine the angular deflection full scale. So, finally, steady state deflection is your theta equal to I square upon k into dm upon d theta. So, dm upon d theta is 0.0035 10 power minus 6 upon pi upon 180, that comes 0.2 into 10 power minus 6 Newton meter per radian, and deflection theta equal to 20 square divided by 10 power minus 6 into 0.2 into 10 power minus 6 equal to 400 into 0.2, that is 80 degree. Now, coming to example 6, a 150 voltmeter moving iron voltmeter is intended for 50 hertz, has a resistance of 3 kilo ohm. Find the series resistance required to extend the range of instrument to 300 volt. If the 300 volt instrument is used to measure a DC voltage of 200 volt, find the voltage across the meter. So, R m equal to 3 kilo ohm, V m equal to 150 volt, V equal to 300 volt. So, as V equal to V m 1 plus R s c upon R m. So, from here we get R s c equal to 3 kilo ohm, and voltage across the meter is 200 volt measurement. So, measure voltage is V equal to V m 1 plus R s c upon R m. So, getting from here V m is 100 volt. Coming to example 7, for a certain diameter ammeter, diameter type ammeter, the mutual inductance M varies with reflection theta equal to M equal to minus 6 cos theta plus 30 millihenry. Find the deflection torque produced by a direct current of 50 microhenry millihenry corresponding to reflection of 60 degree. So, the torque of this electrodynamometer is T d equal to I 1 I 2 dm upon d theta or I square dm upon d theta, where M is equal to minus 6 cos theta plus 30. So, dm upon d theta is 6 sin theta plus 30 millihenry, and dm theta equal to 60, that is 6 into sin 90, that is 6 millihenry upon degree. So, T d equal to I square dm upon d theta, that will be equal to 15 into 10 power minus 6 Newton meter. Now, coming to example 8, the inductance of moving iron ammeter with full scale deflection of 90 degree at 1.5 ampere is given the expression L equal to 200 plus 14 theta minus theta square minus theta cube microhenry, where theta is deflection of radian from 0 to position. Estimate the angular deflection of pointer for a scale of 1 ampere, that as given L equal to 200 plus 40 theta plus minus 4 theta square minus theta cube microhenry. dl upon theta will be theta equal to 90, putting the value 40 minus 8 theta minus 3 theta square. So, dl upon d theta at 0 equal to 90 will be putting the value 20 microhenry radian. So, as theta equal to 1 upon 2 is I square dl upon d theta. So, getting value it will be k spring constant will come 14.32 10 power minus 6 Newton meter per radian, and deflection is for I equal to 1, theta will be putting the value equal to here. So, theta comes here typically 1.08 radian or 57.8 degree. So, there are some unsolved problem you can solve in the similar manner what we discussed, and these are the reference from which we develop this material, and thank you very much.